Hello everyone, welcome back to Off by 1 2025. My name is Sherry Ann and I'll be your MC for the second half of the day. So it is now my pleasure to introduce our next speaker, Georgy Kucherin. Georgy is a researcher at Kaspersky's Global Research Analysis team and a student at Moscow State University. He specializes in reverse engineering and malware analysis and worked on the attribution of the SolarWinds attack, as well as research regarding multiple APTs such as Twirler and Lazarus. So today he'll be giving his talk, Speed Up Your Reverse Engineering with the HRTNG plugin. Let's give a warm round of applause to welcome Georgy on stage.
Hello everyone, my name is Georgy Kucherin, and I reverse engineer malware at Kaspersky's Global Research and Analysis team. In this team, we investigate complex malicious campaigns, such as the ones orchestrated by state-sponsored actors. Speaking of such campaigns, they sometimes involve use of zero-day exploits, and over the years, we have managed to capture in the wild and report to major software vendors more than 30 such exploits. However, apart from investigating malicious campaigns, what we also do is develop several community-oriented projects designed to make reverse engineering a simpler, faster, and less tedious process. As part of these efforts, we develop a plugin for IDA Pro, the framework many people use for reverse engineering every day. This plugin is called HRTNG, which stands for Hex-Rays Tools Next Generation, and its source code is available on GitHub. But before I tell you how exactly our HRTNG plugin makes reverse engineering way more efficient, let me talk a bit about its history. Its development started back in 2016 when we at Kaspersky forked an open source IDA plugin named Hex-Rays Tools. That's why we named it Hex-Rays Tools Next Generation. And over the years, our internal fork of this plugin has been receiving lots of features. It was something that we lacked in IDA while reverse engineering: structure recognition, code deobfuscation, data decryption, and so on. Last year, we published the source code of our plugin on GitHub under the GPL v3 license, giving members of the community the right to copy the code, make changes to it, and publish the changes made. At the end of last year, we also submitted our plugin to the Hex-Rays annual contest, and at the beginning of this year, it was announced that HRTNG scored first place in this contest. So, to demonstrate how HRTNG can be helpful during reverse engineering, today we'll be analyzing a sample of a commercial spyware named FinSpy, also known as FinFisher. This spyware started being deployed more than 15 years ago, and its samples are notoriously known for containing lots of creative obfuscation techniques. This spyware is available for many platforms like Windows, macOS, Linux, Android, iOS, and even old BlackBerry phones. Today, we'll be reverse engineering a Windows sample of this spyware. And while I acknowledge that some of you may not be familiar with Windows internals, let alone internals of the x86 architecture, for example, if you're a mobile device researcher or a student, I'll explain all the necessary details along the way. And for those of you who know a bit more about Windows internals, I prepared some swag to give out. I'll be asking questions during my talk, and whoever answers them will get prizes. While answering the questions, please make sure that I see who gives the answer. Now, without further ado, let's get started. So, our sample is located in this folder. And this is the file, and let's first view its contents in a hex editor. I type hex dump, -c, and then I type the name of the file. And I use the less utility. And now, by looking at the code, I see that the first 2 bytes of our sample are 4D5A. Now, my first question, could anybody actually tell me what this sequence of bytes means? What can we guess about the sample when we see it? Yes? Sorry? Yes, executable file, correct. You get this socks over here. So, yeah, the bytes for D5A are the magic bytes for PE files. And we may make a guess that this file is a portable executable. Now, let's try to load it into IDA. So, we open IDA, press OK, open the sample, and in this window, IDA asks us to specify the file type. But unfortunately, while we saw that the first 2 bytes of our file are 4D5A, IDA doesn't allow us to load the sample as an executable. It only allows us to load it as a binary file. And we have no choice but to do that. We press OK. And here we press yes. I want the sample to be disassembled as 32-bit code. Now you see, immediately when we started analyzing the sample, we get something wrong. It's not what we expected, because we expected a binary file. And while IDA is auto-analyzing the file, well, I'll tell you why we get so many difficulties. Well, FinSpy samples are commonly deployed through zero-day exploits, and over the years we have been capturing these exploits along with other vendors from the community and reporting them so that these exploits can no longer be used by actors. So the adversary doesn't want those exploits and the malware behind it to be uncovered. That's why we get so many difficulties. All right, the auto-analysis has now finished, and down below we have the first bytes of our file. Now, when dealing with a plain binary, what I usually like to do is just try to disassemble its first bytes. Let's do this. I press C, and here we have some valid assembly code pop up. Now, once I see that I indeed have assembly code here, well, we can say that this malware is not a PE file. It is a shellcode disguised as a PE file. And now that we have confirmed that this data is actually code, we should mark the segment with this code as executable. I press Edit, Segments, Edit Segment, and I tick all the permissions for it. Readable, writable, executable. And I press OK. Now let's start analyzing the code. Specifically, these first 4 instructions. Now, if we look at the first 2 instructions, we can see that the byte representation is 4D5A. These instructions, they do not do anything useful. They are simply needed to disguise the shellcode as a PE file. And as for the 3rd and the 4th instructions, they move the value 1 into the AL register, and then they push the value of the EDX register onto the stack. Now let's deal with another sequence of instructions, which is right here. Firstly, we see some constants being assigned to the ECX and EBX registers. And afterwards, we see this subsequence of instructions, FLDZ and FSTNF. Now, anybody here familiar with the x86 architecture? Can anybody make a guess why the malware needs to execute these instructions? Yes? Yes, for position-independent code. And you get this cup. So, well, I'm going to explain how this works. The first instruction, FLDZ, is simply used to load the number 0 onto the floating point unit stack. And then the next instruction, fstn, can be used to store the internal state of the floating point unit into memory. If we consult the x86 architecture documentation for this instruction, we can see that this state is represented with the data we have in the picture. If we convert what's in the picture into a C structure, this state will look like this. And now we see that after the fstn instruction, we execute a move instruction which takes the value from the ESP-10 address to the EDI register. And if we match the addresses in our structure, we can see by calculating offsets that the address ESP-10 corresponds to the FIP structure member. This structure member contains the address of the last executed floating point instruction, which is FLDZ. So the malware gets the address of this instruction, it gets an address inside the shellcode. In other words, the sequence of instruction is needed to get the value of the EIP register or the program counter, as some of you may call it. Now, let's look further into the code. Let me continue defining instructions right here. And what we see is a loop. It involves XOR and roll operations, implying that we have something decrypted. And the XOR key used for decryption is assigned in this instruction, move EBX. As for the number of bytes to be decrypted, it is stored in the ECX register. Well, this is the loop, and to continue our analysis, we need to somehow decrypt the data which is handled by this loop. As for the data itself, if we scroll below, we see some junk instructions over here. These constants don't make sense, the instructions also don't make sense, so we undefine them, and we see some bytes resembling encrypted data. And that's the reason why the malware needed the address inside the shellcode, to be able to get an address of this encrypted data. So now we have to decrypt this. And speaking of decryption, it can be done in multiple ways. For example, you can write an either Python script or a standalone program to do decryption. But today, we'll be doing decryption with the HRTNG plugin. It implements a data decryption function, and HRTNG already implements many popular encryption algorithms used in malware, such as XOR, RC4, or AES. And it's also deeply integrated into IDA. For example, if you want to decrypt data, you can specify the encryption key as an address in IDA database, and HRTNG will automatically get the bytes stored at this address and use them as the key. Now, let me show you how decryption works. Firstly, we need to highlight the data, we need to select it. To do that, I press Alt+L, and I scroll down until the end of the file. Then, I define the encrypted payload as an array. I press Shift+*. I press Enter and confirm that I want the data to be converted into an array. Now, I right-click on the array and press Decrypt Data. In this window, I need to specify the encryption algorithm. In the case of our algorithm, it is implemented under the name custom. By the way, it's very easy to add custom algorithms to HRTNG. You open the decrypt.cpp file from the source code and write whatever algorithm you want using the examples provided in the file. There are lots of them. And the code for our decryption algorithm, in our case, takes just 2 lines. Now, then, as we can see, the number of bytes to be decrypted, HRTNG gets it automatically. And as for the key, we need to specify it. We saw it assigned in the EBX register. Now we press OK, and IDA prompts us to patch the data, which we do. Now, if we undefine the array and define it as code, we can see that we have successfully decrypted some instructions. Let's look at what's happening inside them. We see a jump being performed. It depends on the value of the AL register. It is set to 1, so the jump if not 0 branch is taken, and we get a jump to the following code. We see more assembly instructions, specifically these 3 instructions: move EDI EDI, push EBP, move EBP ESP. Now, anybody can tell me how this set of instructions is typically called in assembly? No one? Yeah, the function prologue, that's correct. So since we're dealing with functions, by the way, you get this towel that I hope you find useful while swimming. So we define this code as a function. And let's look at what happens inside it. If we scroll down through the code, we see this function A9D8. And let's look at it more attentively. We see that its second argument contains a large number. And if we pay attention at its return value, we see that it's a function pointer because, well, we see the v32 variable used to call a function. Now, if we look what's happening inside this function, we scroll down below and we see some structure manipulations related to offsets 3C and 78. Now, anybody familiar with the structure of Windows PE files will immediately recognize these offsets. The offset 3C is used to get an offset to the PE header, and the offset 78 is used for getting an offset to the PE export directory. Down below, we see this function getting called A924. And if we decompile it, we see this code. Now, based on the code you see, can anybody recognize the algorithm implemented here? Yes, CRC32. That's correct. Your prize is this bag. So, what we see is some manipulations with the PE header, as well as calculation of hashes. If you're familiar a bit with malware research, then you'll recognize that by doing these actions, the malware implements a technique called API hashing. It's a defense evasion technique that allows you to stealthily call Windows API functions without explicitly mentioning their name in the code. How it works is, let's say you want to call the ntprotect virtual memory function stealthily. What you do is calculate the CRC32 hash of its name and store it somewhere in the binary. Then, at runtime, what you do is iterate through available Windows API functions, and you take a hash of the name of each function. You do that, and this needs to be done until you see that the value of the hash matches the one that was previously calculated. I mean 0x5c, 2d, and so on. And once you found the correct hash, it means you found the address of the function. Now, this technique is very commonly used in malware, and that's why HRTNG implements a functionality allowing to defeat it. This plugin implements also many common hashing algorithms used in malware, such as ROS13, CRC32, FOV1A, and many others. Now let me show you how this functionality works. To use it, we first need to import the Windows type libraries. To do that, I press Shift plus F11, press Insert, and I type ms SDK win10 to import the Windows SDK type libraries. I also need the internal type libraries. I press Insert, and I type nt API win10. Afterwards, I head back to the function where I saw the hashes, and I press Edit, Other, turn on API hashes scan. In this window, I choose CRC32 as our hash, as you managed to guess correctly, and press OK. Now, if I refresh the decompilation, press F5, I see that instead of these V variable names, IDA now displays the names of functions that correspond to the hashes. But also note that thanks to HRTNG, IDA has been able to automatically recognize the amount of arguments of the library functions as well as the types of the arguments. Thanks to that, well, it's very useful because you don't have to, for example, search for the documentation if you want to find out what, let's say, the third argument of the NT-protect virtual memory function is. Now, if we look down below what happens with the code, we see this loop being executed. Well, in the loop, we see that the malware searches for some signatures. These signatures are MZ and PE. We have to read these letters in inverse. And by the way, about the loops, if you noticed, HRTNG draws a gray line for the starting and for the opening and closing curly braces for the if conditions and loops. And also, if you press the brace key, then you'll be able to switch from the let's wait for the screen to reappear. You'll be able to switch from the starting and ending braces. And this is very convenient because you may just use it to skip code that you may not want to analyze. So, based on what we saw, well, the MZ and PE signatures, they identify PE file headers. And thus, by looking at this code, we can infer that the malware is supposed to load itself by using the headers inside it. This is especially the case because we previously saw some memory or operation functions like NT-protect virtual memory being used. Now, well, we already saw the MZ signature. It was right at the beginning of our file. And if we scroll down below, we see the signature PE. And this may be the place where the PE header is stored. To confirm it, let's apply the PE structure, the PE header structure, to these bytes. I click Structures, Insert, Add Standard Structure, and I type image NT headers. That's how the PE header structure is called. Then I go back to the memory, press Alt+Q, and I select the image NT header structure. And if we look at the values, we see that they do not contain any junk. This means that the PE header has been applied correctly. So now what we have to do is manually load the executable file into memory so we can further analyze it. We do it because IDA previously failed to perform the loading correctly. Speaking about loading, this process involves two steps. First of all, we need to map the executable file at the correct address in the IDA database. This address is called the image base address, and it is stored right here in this field. So what we do is we copy this value, press Edit, Segments, Rebase Program, and we type the address. Now, as you can see, our program is based at the correct address. And afterwards, we need to find out what library functions the malicious payload imports from the operating system. Now, in the case of PE files, this information is stored in a structure called the import directory. And we can access this directory through the PE header. Here it has an array of the so-called data directories, and the import directory is the data directory with offset 1. So this is offset 0, and this is offset 1. We have this number right here, 1240C, and it is a relative virtual address. It's an offset relative to the image base of the file. Now, to go to the address which matches this offset, what we can do is simply add the image base, which is 400,000, to this value, and we should get something like 41240C. And this is the byte with import information. However, let me show you a trick that allows you to avoid doing these calculations all the time. You can just make this offset clickable, so that it turns into an address in IDA. To do that, you head to the structure window and expand the definition of the data directory structure. You click on the virtual address field and press Ctrl R. You press yes here, and in the window that shows up, you make sure that the option Use image base as offset base is ticked. Then you press OK, and now note that IDA annotated the member field with offset RVA, relative virtual address. Now, if we examine the bytes, we'll find out that the offset became clickable. We get the same address with input information. Now, this input information is stored as an array of structures called image import descriptors. Again, to apply the structure to memory, we need to load the structure into IDA. Structure window, insert, add standard structure, I type image import descriptor, and I go back to the window, and I press Alt+Q, and I apply the import descriptor structure. Now, I mentioned we're dealing with an array of the structures. We need to continue defining the structures until we see a structure consisting entirely of zeros. Now, these ones are non-zero. These contain non-zero values. We continue adding non-zero, 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 0. So these are all import descriptors available in our program. Now, let's compare the contents of these import descriptors with what we have in the PE file documentation. The information about function names to be loaded is stored in the first member of the structure, called original first thunk. But in our sample, we have this original first thunk field set to 0, which is very strange. Now, can anybody give an idea of why we have this inconsistency? Why do we have zeros here while we should have some information about names? No one? Okay. So the issue is that while we are dealing with PE structures here, the file we are analyzing is not an ordinary PE file, it is a shellcode. And what attackers did, they tampered with the structures, they changed it a bit to make it more confusing for analysts to analyze the file. And to find out where the information about function names is stored, we need to examine other fields of our structure. Now, I'm talking about specifically the second to last and the last fields. These fields are as well relative virtual addresses, offsets, and we apply the same trick to make them clickable. Expand the image import descriptor structure, click on the name field, press Ctrl R, press yes, make sure this is ticked, and press OK. We do the same with the first thunk field. Press OK, and now if we look into the code, we see that the offsets became clickable. Now, the second to last offset is supposed to contain the names of libraries from which the malware imports functions. They look all good. However, if we look at the last field, which points to a memory storage holding the function addresses after they are resolved, we see some weird bytes here. But if we start defining the bytes as D words started to bit integers, we see that HRTNG starts converting them into function pointers. What actually happens here is that the malware, as I said, implements a custom input resolution procedures. It looks at these values that we saw, which are CRC32 API hashes. And for each hash, it matches the hash with its corresponding function address. And then it overrides each hash with the function pointer. Remember I said that this field is supposed to contain pointers to imported functions. The malware does exactly that. It places these pointers. And note how HRTNG has been able to automatically recognize these hashes in memory as we define the double words, as well as identify the correct function arguments, the count of arguments, and the types. So now, when we dealt with imports, when we found out how the malware loads functions from the operating system, it's time to look at the entry point function. Again, it is located in the optional header, in the PE header. This is the offset, the relative virtual address to the entry point function. We do the same trick. Structures. I need to select the optional header structure, which contains this member with the entry point offset. Press Ctrl R, press yes, make sure use image base as offset base is set, and press OK. Now we can go look at the entry point function. If we try to define it as a function, we see that either colors the instructions, the addresses in red, which means either failed to define the function here. To find out why, let's look at the code below. Over here, we see the registers push ESI, the registers ESI and ECX pushed onto the stack. And right after this, we see lots of mathematical operations performed with the ESI register. Additions, subtractions, XORs. But if we look down below, towards the very end of these operations, we see that the malware pops the values of the ESI and ECX registers from stack. And this results of the mathematical operations that are not used anywhere. This means that all these operations are useless. They're just junk code. And when we are dealing with junk code, we need to replace it with a NOP instruction to make sure that IDA can proceed with the analysis of the sample. This can be done easily with HRTNG. We select the junk instructions, scroll up until the very start, and the junk instructions start with the SBB instruction. Then we press Edit, Patch Program, Fill NOPs. We press OK here, and we see the junk instructions have been replaced with NOPs. Now let's continue and see what happens after the function executes all those junk instructions. We scroll down, there are lots of these NOPs now in the code. And over here we see that the function makes a jump. If we follow it, we see more jumps. JAGBE, JZGNZ, JOGNO, and so on. Now, if we look at these pairs of jumps we saw attentively, we can see that these pairs of jumps, they all branch to the same address. And furthermore, we can observe that these conditional jumps are opposite to each other. JZ, jump if 0, JNZ, jump if not 0. And because of that, one of the two conditional jumps is always executed. Furthermore, as we see that the jumps branch to the same address, we can say that each pair of these conditional jumps actually constitutes an unconditional jump. It can be just replaced with a jump instruction. But what we are dealing with here is a code flow obfuscation technique. And because of it being present, IDA can't define a function correctly. Well, for dealing with such obfuscated functions, HRTNG has a functionality called decompile obfuscated code. It efficiently deals with similar control flow obfuscations. To use it, what we need to do is to go back to the beginning of our function and press L plus F5. In this window, we press OK. Now, HRTNG started analysis of this function, but now we see that it says, please make code, press escape, and try decompiling again. There has been some error, and once we press OK, we see some junk code. Again, it doesn't make sense. Let's follow the cross-references to see where this junk code is called. Look at what we have. We see a comparison of a functional argument with the value inside EAX. And the value inside EAX is first XORed with itself, which sets the EAX register to 0, and then 1 is added to it. So essentially, we compare the argument value is 1, and if it's not 1, we have a jump if not 0 instruction. Then we branch to junk code. Again, this is an anti-analysis technique. We need to get rid of it. So we highlight, we select the two junk instructions, we press Edit, Patch Program, Fill knobs, and press OK. And once we're done with that, we decompile the function. And if we scroll down through what we have, we see that we got at least something readable. But analysis of this function is actually not straightforward. If you do it, and if you compare what you see with what's available on the internet, you'll eventually be able to find out that this code represents the engine of an obfuscator named FinSpyVM. This obfuscator is based on code virtualization, and breaking virtualizing obfuscators is not an easy thing. We'll not be studying how to do this today, and if you want to learn more about that, please feel free to read one of the many papers on how to deobfuscate FinSpyVM. In this talk, we'll be using a ready-made script for deobfuscation. However, there is an issue with it. To make this script work, you need to provide it with opcode numbers, the identifiers of each opcode. These opcodes of virtual instructions are defined as indices in the table with functions that defines the virtual instructions in the x86 assembly language. Let me explain how this works in greater detail. So this is this table, and we see we have functions in it. Let's take a look at this function. We decompile it. You see here a shift left operation. This is a shift left virtual instruction. And in this table, it has the offset 1. This is offset 0, this is offset 1. So what we need to do in our deobfuscation script is say that the SSL virtual instruction, the shift left instruction, corresponds to opcode number 1. Now, well, we have to do this all manually because in each sample, the order of these virtual instructions is randomized. And what we have to do as an option is to manually look at each of these virtual instructions and see what they do. But if we think about how we can automate it, we can use function recognition. Well, IDA has a default function recognition engine. Anybody recalls how it's called? How the default function recognition engine is called in IDA? Nobody remembers? Yes, Flirt, that's correct. And you get this mug over here that will help preserve the temperature of your drinks. Well, the issue is that this function is obfuscated. And because of the obfuscation, the flirt recognition engine doesn't work very well. It's based on assembly, and if you change the two assembly instructions or do something similar, the signatures won't work. To perform function recognition in case of obfuscated code, well, HRTNG implements its own function recognition engine. It is based not on assembly language, but on microcode, which is an intermediate representation generated by the Hex-Rays decompiler. It is optimized, and because of that, it is more robust against obfuscations. Now, using this engine is very straightforward. What you first need to do is export the function names from a sample that you have already finished analyzing. And then you have to load the signatures with the function names into another sample. Let me show you how this works. Press File, Load File, msig file. I head to the msig directory, and I apply the signatures. And now, if I decompile this function again, let's wait for the text to appear on the screen. Well, I just said that this function, well, let's wait it to appear once again. This function matches signature as a shell, shift left. If we do it with another function, the one at offset 2, we decompile it, JB, jump if below. And we see that the JB instruction corresponds to opcode number 2, and in our Python script right here, we mark that JB is number 2. Now, we won't, of course, will be filling all the opcode numbers right now. We'll just use the ready-made script for the obfuscation. File, script file, finish by the obf. Well, I apply the script, and now if I decompile the entry point function once again, we see some clean, unobfuscated code. It's already ready for analysis, and we see that this code implements it uses lots of API functions. Networking, file creation, registry manipulations. We see, let's wait for it to reappear again. Well, yeah, SSL keylog file, file writing, something with window messages. These functions are commonly used for keylogging. So basically, if you look at this implant, you're going to recognize, after doing all this stuff, after filling the values, after decompiling, you're going to recognize that it is an espionage implant that's able to do many things: file system control, registry management, keystroke interception, PGP key theft, and many more things. Now, before I end my presentation, let's summarize what we've done today. We've decrypted code, done API hash analysis, deobfuscated control flow, performed function recognition, and even deobfuscated a virtualizing obfuscator. And all this we've done in 40 minutes. It wouldn't have been possible had it not been for HRTNG. I hope that by this example, I managed to convince you that HRTNG is a really helpful tool in reverse engineering. Please download this plugin from GitHub. It's available in the form of source code as well as compiled binaries for Windows, Mac OS, and Linux. And before we end, I would like to give a huge thanks to Sergey Belov, who is my coworker at Kaspersky and who created and who actually develops HRTNG. Without 8 years of his work, well, this plugin, its development wouldn't have been possible. Thank you, and if you have any questions, please ask them either now or in the conference hall. I'll be here throughout today and tomorrow. Thank you very much.
Thank you, Georgy, for your very insightful talk. So we do have time for one question, and Georgy has mentioned he does have prizes for Q&A. So does anyone have any questions to ask?
Yeah. Whoever asks a question gets a prize. Yeah, you can get a second one. Oh, well, about the question, yes. I'll explain about this later. Yeah. So, any technical questions? Okay. MD5 of the file, yes, it's available on VirusTotal, and there was also a recording. I think I showed it during the recording. Yeah, so the file hash is right here. So sorry, you have to retype it, but it's available on VirusTotal. You can download it from VirusTotal.
So we do actually have time for one more question. Yeah.
Can you hear me?
Yeah.
Yeah. So the main goal of this is obfuscation of code. In what areas do you think that this would be, most commonly used? Like, in where are the areas where where the obfuscation of code would be most impactful?
Yeah, thanks for the question. Well, obfuscation is used not only in malware. It's firstly used in malware, but you have it used in many other things. Well, whenever software developers want to protect their code from being reverse engineered, they use it. It's implemented in the Windows operating system, in the patch guard component, for example, if I'm not mistaken. It's implemented in many commercial software, for example, in games, which have anti-cheat systems. So obfuscation is used in many places, both in malware and legitimate software, and for a reverse engineer, if you want to find out where the vulnerability in the software is, and if it's obfuscated, you need to first break the obfuscation to analyze the code statically for vulnerabilities. So it's used a lot. And our plugin is indeed very helpful when dealing with many obfuscations. It has many more features than I showed today. Well, you get a full list on GitHub, come visit the page, and learn more about it.
All right. Thank you, everyone. And thank you, Georgy, once again for the talk. So let's give him a round of applause once again.